So good afternoon, everybody. Thank you for joining our webcast today. My name is Frank Thomas. I'm with Additive Corporation. Today we're broadcasting from a facility in Youngstown, Ohio. The name of the facility is called the Youngstown Business Incubator. This is our additive manufacturing lab in Youngstown, Ohio. Many times it's referred to as YBI. So YBI, it turns out, is the headquarters of America Makes. For those of you that aren't familiar with America Makes is a national initiative for additive manufacturing. So lots of different companies affiliated with America Makes, and they help promote some of what we're doing with some of the technology that you're going to be seeing today. So it's really exciting, and we're delighted that you joined us today. What we've done is we've put together a use case that is pretty much a real-world use case that happens fairly often here at Additive. It's based on a customer experience that we had some time ago, and we thought would resonate with all of you in terms of being able to see the different steps of the process. And there are various pieces to what we're going to be showing. I'll explain all of that to you here in one moment. Each one of these pieces could be a standalone solution, if you will, depending on what you're looking to optimize. So part of what we're going to be showing is a design optimization process, so we'll get into that here shortly with you. Then we're going to feature our metal manufacturing capabilities here, and we'll show you some examples of that and show you some parts and some customer examples there. And then we're going to get into 3D scanning. The 3D scanning and the use case that we're going to outline today is for inspection. Of course, 3D scanning can be used for a variety of things. We're going to focus on inspection today. Okay? So with that, let's cut over to the PowerPoint, if you would, and we'll run through kind of the agenda. So the title of the presentation is called "The Future of Additive is Now." And the agenda kind of looks like this. We'll go through some quick introductions. We'll highlight design and optimization for additive manufacturing. We're going to, as I mentioned earlier, we're going to show you really focus on the additive manufacturing, the metal 3D printing process here. And then we're going to get into 3D scanning for part and quality review. So the use case outline, just so that you can kind of follow along a little bit, kind of looks like this. So we invented a fictional company. We're going to call it Adventure Incorporated. And it turns out that Adventure Incorporated is, they manufacture lightweight competitive off-road bicycles. And as you might have guessed, Adventure is sensitive to the weight of their bicycles. Since they're used for competitive applications, they want them to be very, very lightweight, but they also need them to be very, very strong, because if they're taking jumps and going off-road, they need to handle high impact. So in our example, Adventure has identified several components for lightweighting and additive, and they would like to try additive in their customer process. So these would be end-use parts in this example. So we're going to focus on one of those components. Of the several, we're just going to focus on one. So what Adventure would like to do is that they'd like to use generative design in CAD to lightweight and optimize the parts. So kind of the concept there, and Bart will get into that here more in a couple of minutes, but the general concept of generative design is to minimize the mass of the part but maximize the strength at the critical attachment points where strength is needed. Adventure's CAD platform is something called 3D Experience by Dassault Systems. We'll talk a little bit more about that here momentarily. And the part is going to be optimized for strength and minimize the weight of the part. And we'll explain that to you here shortly. Then the part is going to be 3D printed in metal on the Markforged Metal X. So my associate Tim and Jeremiah are going to get through walking through what that whole process looks like with you. And then afterwards, we want to 3D scan the part to validate that the part meets their dimensional accuracy. So how do we do that? What does that process look like? So the part that we've identified for our use case is this component of the bicycle. It kind of attaches the frame to the back end of the bike, and it's attached to a shock absorber. So it's a pretty critical component. The component here in green that you see is the way that the part is manufactured today subtractively. So what we're going to do is we're going to explore the process of creating this part additively and minimizing, reducing the weight of the part. First, a couple of words about Additive. Additive, we've been around for about 13 years now, and there are various components to our business that starts with CAD, so the CAD, the PLM, the simulation tools that are part of that, and they all get wrapped by a data management utility, something that is called a 3D Experience Platform. So the 3D Experience Platform is the wrapper around everything from design to simulation and program management, project management, and helps with collaboration, especially in this day and age as more and more of our customers are looking to remotely connect and engage resources from different parts of the country. This can be on-premise, it can be cloud-based, very, very flexible. So that's part of the solution that we're going to be showing you today. The other parts of the solution are based on 3D printing platforms, something by a company called Markforged, which is based out of Boston. We'll talk a lot about Markforged here briefly, featuring again their metal printers. And then we're going to be talking about 3D scanning quite a bit. We offer a solution by a company by the name of CREAFORM, and we've been working with them for going on 10 years. They make some brilliant technology for 3D scanning and inspection, as well as reverse engineering. So with that, we're going to get right into our technical presentation on the generative design process review, and we're going to cut to the video with Bart at this point.
Hello everyone, my name is Barton Schenk and I am an application engineer for the Additive Corporation. Thank you for joining us today for our presentation about how the world of product design is evolving in order to keep up with the latest technology in additive manufacturing. My hope is, by the end of this session, you will have a solid understanding of how the latest design tools can be leveraged by any company who is looking to or already has invested into additive initiatives. Today, we will be using an example part from a real bicycle company that was used as a successful proof of concept for their use of additive manufacturing and generative design. But before that, let's start with some basics about the world of additive. Here is the general flow of today's session. We will start by outlining some common business goals for those who are using additive manufacturing. The subsequent material is all about how additive is changing the world of design with new tools and processes. Finally, we will show you how we can optimize and make our example part. Why is the future of additive now? To better understand why, we need to understand some of the goals of companies who are implementing additive strategies within their businesses. In my experience, there are three main goals that these companies have in common. They are part lightweighting and topology optimization to print parts faster with less cost. Automated production to simply set things up and scale up as you need to go. And flexible manufacturing, being able to offer a wide variety of products with quick turnaround time. The most common goal is lightweighting. Companies need their parts that are lighter but are just as strong as the legacy components. The two other business drivers are related to the automation potential and flexibility of additive. This is true especially when compared to traditional subtractive methods. Now let's see how this can be achieved. In today's session, we will focus primarily on part and product lightweighting and optimization. As you know, many industries, such as aerospace and transportation, rely on weight reduction to reduce their products' cost to own and operate. Please keep in mind that this is just one of many benefits of this new design approach. In recent years, software vendors have been developing specific tools to enable designers to create new versions of legacy parts. The new designs are fully validated with their specific load conditions, and an organic and optimized shape can easily be achieved. This is accomplished by incorporating FEA and topology optimization into a predefined design workflow. The images along the bottom of the screen are examples of how designers can go from simple space reservations to unique organic design variants. With traditional subtractive methods, these unique topologies would be very difficult to manufacture, or potentially impossible. However, with today's 3D printing technology, these parts can be used as anything from functional prototypes to full-blown production parts. As a result of the need for design optimization, a new design discipline has emerged to lead the way for additive manufacturing processes. This process is called function-driven generative design. It is truly a new way to design. The naming is appropriate as the general idea revolves around using a part's functional specifications and its design space reservation to help determine the optimal part. Some of the generative design software tools can even propose new shapes based on your desired manufacturing process. This can include milling, casting, or 3D printing. While there are multiple tools that exist in this discipline, for today's presentation, we will be using CATIA 3D Experience on-cloud solution. The 3D Experience role that will be used is called Function-Driven Generative Designer. We will soon see how solutions like CATIA on the 3D Experience platform can combine solid modeling, FEA, and surface modeling within a single environment to allow designers to become optimization experts. In the design world of yesterday, optimizing a part's topology or overall shape while maintaining its strength and functionality was a very linear process. As you can see in this diagram, there are a minimum of 3 different people involved in multiple tasks. Data must be passed back and forth for each design iteration. This consumes a lot of precious time. Also, everyone stays in their own proverbial silo and only deals with their data set within their own specific software. Now, each of these steps can be done by one person with a new generative design workflow. Here is the workflow for the new discipline of generative design. As you can see, this process starts and ends with a single designer. Starting in the top left, you can see how the legacy part is made into a design space model, meshed for analysis, and then optimized. The designer enters the load specifications through an intuitive workflow assistant to make sure all relevant information is present. The user can also define how many variants they want to generate and use multiple load cases in their optimization. Robust comparison tools then allow the user to review their design options in a dedicated tool called Trade-off Study. Once the optimized part is chosen, detailed surface modeling and refinements can be made, and the final part is ready to be printed. Now we will begin looking at our example part for optimization. As mentioned before, this is a suspension rocker link from a real bicycle OEM. The image on the left is the traditional casted part. The company has identified this part as unusually expensive to produce due to its unique shape. Therefore, we were asked to help this company explore whether parts like this could be optimized and additively produced. The next video will show the steps taken in order to optimize this part's topology and get it ready to print. Here is the legacy data that we are working with. On the right is the legacy part by itself, and the left is the part in its assembly context. Let's get the optimization started. We will use the assembly context to determine the design space or available volume that can be used. The shape will be the starting point of the generative design process. Within the generative design application, a design study is started. This brings up the Setup Assistant, which will guide the designer through some of the analysis setup portions of the design process. As you can see, there are just a handful of guided steps that are performed in order to get an optimized model. From initial model configuration, constraints, and load cases, to manufacturing constraints and thermal conditions. These new applications have clearly been tailored for the additive industry. Next, we begin to define the functional specifications of the part. The Guided Workflow Assistant allows the designer to easily create and modify connections, constraints, and virtual parts within their optimization analysis case. As you can see, the load case conditions are incorporated directly into the model. By placing these loads and forces onto the design space model, we are prepping the generative design engine to compute multiple variants that will serve the same functional purpose. Here we see the creation of multiple load cases, building even more intelligence into this model. With our load cases set, we are now ready to mesh the part and run our initial part analysis. The mesh parameters are also controlled in this step. They can be automatically created, or you can key in your own values. A 3D mesh is generated within the design interface, and we are getting closer to being able to run our optimization. After a quick verification by the Setup Assistant, we are ready to run the first analysis case. This initial analysis run will be the baseline for the topology optimization in the next step. Keep in mind, these analysis calculations can be run locally or on the cloud. As soon as the calculation is complete, the results are ready to be displayed. The displacement and deformation models are the drivers that help combine FEA and iterative topology optimization. With the initial analysis run completed, we are now ready to run our first optimization case. Before we run the optimization, we must first define the functional regions of the part. In other words, the areas of the part that cannot change their overall shape. We then partition the design space so that those functional regions remain intact during our next analysis. As we prepare to launch the topology optimization job, the user can define how many iterations will be run. Of course, the best results come from more iterations. However, please keep in mind that more iterations takes more time. The user can also define their target mass, which is the desired percentage of the original part's material that they believe is ideal. In this case, we're using 75%. The Run button is clicked, desired iteration count is defined, and the job is ready to begin. On average, running between 50 and 100 iterations takes around 15 minutes or so on a model like this one. Once the job has run, a convergence model can be displayed to easily visualize what design variants you have to work with. CATIA can then automatically generate a solid model that best approximates the shape that you choose. Here we can see such a model. Once the user gets to this point, it is time to use the best-in-class surface reconstruction tools in the industry. Here we can see the user creating strips using the Imagine and Shape engine that CATIA surfacing is based on. In this accelerated view, you can see how much control the designer has in order to best match the design variant that was chosen from the generative design workbench. Another key advantage here is the direct surface modeling techniques that can be used with a subdivision surface, like this one. As we jump ahead, you can see the one-click process for taking a subdivision surface and creating smooth and printable geometry. This process can be repeated as needed until the part has been fully optimized and ready to be sent to your printing software. Here is the part ready to print, and we are ready to go. Next, we will be showing you how this part is printed, cured, and inspected on the Markforged Metal X printer. Thank you all for your time, and have a wonderful day.
Hi there, I'm Tim Weatherford, 3D printing line of business manager with Additive. And today we're going to show a short video here of a clip of the equipment and actually the process that we use to go through.
Hello, my name is Jeremiah Creighton. I'm the Markforged Metal Certified Technician with the Additive Corporation team. Today we're going to be discussing the three-part process with Markforged Metal System. There are three steps with the Metal X process: printing, wash, sintering. Starting with CAD, we have our part designed for additive manufacturing with weight optimization. We have exported and uploaded the part into Eiger. Eiger is a cloud-based slicing software that comes with all Markforged equipment. Parts are automatically configured to the selected material. Metal parts are scaled up to account for shrinkage during the downstream processes. Eiger then slices the part into layers, identifying overhang and needed supports. Eiger will allow you to keep track of the part through the entire process. Okay, before we hit print, I'd like to go over a few more details with the Metal X printer itself. And the way it works, it uses a two-part system. You can see we have two spools here, one of the actual material we're going to use, which is 17.4, and the release material. This works in conjunction for us to be able to remove supporting materials as the part may require them. That being said, the metal printing system is capable of using multiple types of material. You can use stainless steels, tool steels, copper, and Inconel, and there are currently other materials in development. Now that we have selected print, let's touch base on what happens next. Before the print starts, the Metal X maps and levels the bed to ensure the first layer goes down well. The print is done with two materials: the material selected for the part, which is made up of a two-part plastic binder and the metal material, and the ceramic release material, which is extruded as an interface between the part and supports. This is done layer by layer as needed, making these structures easy to remove after being centered. Okay, now that our part's completed, we're going to clear the build plate, and the part now is in what is considered the green state. The part can now be separated from the build sheet, weighed, and moved over to the next step, which is the wash one. All right, here we are at the wash one, which is step 2 in our process. We're going to take our green part, place in the basket, and following the process in Eiger, it's going to tell us the duration of time which it needs to remain in the wash before we can proceed to our third step. Okay, here at the wash one, we have our part that has already been washed and now dry. Again, following EIF will keep you up to date with all of your progress. We can now move the part, which is considered the brown part at this stage, to be sintered in step 3. All right, here we are at step 3, which is our Sinter 2. We can now process our brown part. Placing that all the way back into the Sinter 2, we'll put in place the final part here for safety. Okay, we can then follow the process with the screen of the Sinter 2, and this part usually takes on around 30 hours. All right, now that our Sinter run is complete, which we were alerted to with EIF, again following us through every step of the way, we can remove our part. Thanks to the two materials that the Metal X allows us to print in, the ceramic release material stays in the powdered state, so it'll be easier to remove supports and the piece from the raft.
Thank you, Jeremiah, for the overview. So right now what we want to talk about is how additive can transform your business. We do this by looking at several key areas, lowering your production cost, freeing up your machinist time and talent, improving your quality, reducing your inventory and overhead, shorter production cycle times, and faster development and production scaling. So what do? We move really inventory from physical to digital. We move your production costs, lowering it from typically a high price to a lower cost. Your manufacturing to local from offshore, logistics to last mile from global, and then we do new product development, we speed that up. And basically help with demand planning to make it predictable and uncertain. So here we'll hear from a customer, Caldwell Manufacturing.
At Caldwell, we make components that go into windows and doors that are sold around the world. We've used the Markforged printers to make everything from prototype all the way through low volume production pieces, tools, and fixtures to aid in manufacturing for assembly and/or test and measurement.
In the past, an engineer would need a part made and I'd have to estimate how long it would take to machine that part. Some of those parts could have 40 hours of machining in them. Today, with the Markforged printers, an engineer will give me a drawing and the first thing that comes to my mind is I want to use the printers.
This fixture to machine traditionally would probably cost 5 times as much and take 2 weeks to manufacture. I printed it in a day and they were able to use it that same day.
This is a production assembly. This is a prototype assembly using both composite and metal 3D printers. This assembly allows you to tilt your windows in for cleaning. Having the ability to 3D print our own metal components has really improved our development process.
The similarities between what we'll print in stainless steel and what we would cast in stainless steel is just incredible. That's something we can get in 2 days in our own lab. The hardware we manufacture is what holds the window together structurally, and if that were to fail, it can mean severe damage to a building and major disruption for someone's life. The strength of the 3D printed parts that we get off the Markforged machines allow us to put those parts through the same set of conditions that we would test a production piece. They're real parts that have actual strength.
In this highly competitive world, you need every advantage you can get to produce the parts, do your job, have a leg up on your competition in every single part of the business possible. And 3D printing is huge to help us do that.
Okay, great. So we'll talk a little bit about the Markforged platform. Jeremiah did a good overview of it, but we'll go into the technology. So basically we have a comprehensive portfolio of materials, including composites and metals, which we'll get into. We bring the strength and accuracy, so on the Instatron we're looking at 21,000 pounds plus before carbon fiber reinforced parts actually give way. We're looking at accessibility and easy to use technology. With all the equipment being Industry 4.0, we could have the machines spread out throughout the world and still be able to access them. And also Markforged is bringing innovation to the forefront with our new technology that was just created called Blacksmith. So one industrial printing platform. Our software goes across all the different printers, whether it be our desktop, our industrial, or our metal. So bringing us the full range of plastics, continuous fiber, and metals. We're actually able to build composite and metal parts together. And as I mentioned, the enterprise software is very easy to use, same interface for all technologies. Here we start off from the left. We're looking at our desktop series. Then we go into our production series. And with the metal, we actually have a couple of pieces of additional equipment, which Jeremiah reviewed, which is our wash and our Sinter. Our plastics technology, we have a percentage of carbon fiber, which makes it a lot stronger than ABS, which I'll get into. And we also have in the middle our composites reinforced, and then our metals. Here's a hybrid part, so we're able to utilize composites to lightweight the material, the product, and then we could use metal for wear resistant. In this case, we're using tool steel for the touch pads. Basically, the way our carbon fiber reinforcement or our fiber reinforcements work is much like rebar. So concrete couldn't span a long area before rebar, and now you can see skyscrapers and other applications for long, continuous cement roads. So we're bringing metal strength, durability, and optimized performance with our continuous carbon fibers. This is how the actual product works. So we reinforce the continuous fibers and route them through the part, and then we blend those with the matrix material of our onyx. Here's a strength chart. So basically you can see most printers typically fall into the ABS, which is the second from the bottom line. Our onyx improves that. And then when we add in continuous fibers, whether it be Kevlar, fiberglass, high strength, high temperature fiberglass, or carbon fiber, we bring a different blend of strength and results. So our Metal X platform, it's very safe. It's affordable and it's easy to use. So we can actually utilize 4 to 5 Metal X printers to one wash and Sinter, which actually lowers your cost of ownership. And the way that it works is we print, we wash, then we Sinter the part, and then we have the end result part. Currently our material that are available are 17.4, Inconel, tool steels in H13, D2, A2, and newly shipping is copper, which is very interesting material. We also have in development titanium and 316L, another blend of stainless. And with that, we'll go to scanning the part.
So now comes the fun part of the presentation. We're going to get into 3D scanning and inspection. And for this part of the presentation, we're going to show you a live demonstration of the 3D scanner. I'm sure that many of you on the call have some familiarity with 3D scanning. So we'll run through the process that many of our customers employ, and we'll show you the sample or the process on the part that we 3D printed, and we'll just run through the different steps in the process so that you get to see it and understand a little bit better. You can cut back to the PowerPoint for 1 second. So on the 3D scanning, if you look at the way that inspection plays out in most of your companies, you have a variety of tools. So most people have, we'll call it first generation, is maybe a CMM of some kind. CMM stands for a coordinate measurement machine. Arguably, first generation could even be hand tools, manual inspection, micrometers, and the like. So most everybody has that. Second generation inspection technology we would refer to as a 3D arm, like a ferro arm or a roamer arm. It's still a great tool, and most companies for sure need arms. Third generation inspection gets into scanning. And why is scanning catching on so quickly? It's catching on quickly because it's fast. It's highly portable. If you look at the first generation and second generation technologies, those technologies are not really portable. In other words, I can't take it out to a customer site. I can't use it out on the shop floor. Those technologies need to be in the lab, they need to be in a metrology lab, and that's okay, but they don't have that portability. So the third generation technologies that Additive offers, and we provide this as a service, by the way, is all features portability in support of Industry 4.0. Tell you a little bit about the portfolio. We'll be demonstrating one of the scanners today. The portfolio that we offer is by a company by the name of CREAFORM. And CREAFORM offers a variety of scanners. Why? Because there's no one tool that does everything. So just like a CMM, when we go in to visit a lot of our aerospace customers, all of them are going to have a CMM. Are we proposing that they get rid of the CMM and replace that with the scanner? No, of course not. A scanner can augment what you already have. And especially if you have some bottlenecks in QA/QC, 3D scanning can help expedite the process. And this is the portfolio that we employ. Again, the tool that we would recommend is really based on the type of job. So if I'm scanning something small like the size of a Microsoft mouse or up to something about the size of a car door, that might dictate one tool. If I'm scanning something that starts at the size of a car door and typically goes bigger, again, that could be a different tool. So that's how we gauge things a bit. We'll show you a little bit of this. On the back end, we use an inspection reporting solution. The name of the software is called Polyworks. Now the good news about Polyworks is that Polyworks supports everything. It doesn't care what brand of 3D scanner you have. It doesn't care what brand of arm you're running. In fact, Polyworks even supports CMMs. So the nice thing about Polyworks is that if I teach my programmers how to create my inspection plans inside of Polyworks, on the back end, I can drive CMMs. On the back end, I can drive ARMs. On the back end, I can drive any 3D scanner. A lot of times, our customers are kind of challenged in QA/QC because they've got 2, 3, 4 different kinds of tools, and this person is trained on this tool, that person's trained on a different tool, and they're really not interchangeable. By introducing Polyworks into your organization, now you've introduced that flexibility, and you use the right tool for the job. So to explain to you what we're going to be doing here a little bit today, we're going to take the part that Jeremiah printed earlier, and we're going to pull that part into Polyworks. We're going to pull the CAD that created that part into Polyworks. Then we're going to 3D scan the part, and we're going to pull the 3D scan data into Polyworks, and then we're going to generate an inspection report. So it's kind of a 3-step process. I'll show that to you today. We'll get through it in 3 to 5 minutes. I think for everybody, I think it's interesting to see. Maybe a lot of you have already seen it, but I think it's interesting to see and allow you to determine if or where it might fit in your organization. Let's go back to the video. To me? Yep. Okay. So this is the scanner that we're going to be showing today. This is the handy scan. You'll notice that it's just got a USB cable. It plugs into a USB port of a computer, a laptop computer or whatever. And this is the part that Jeremiah printed earlier for us. So I don't know if we've shown you the part before, but this is what the part looks like that Bart went through the generative design process and optimized the part. Once he optimized the part, the output from that process was an STL, And then Jeremiah took the STL into Eiger, and we reviewed that process with you. He 3D printed the part, and then he washed the part and sintered the part. So now we've got the physical part. So now my job, I'm the QA, QC person in this example, is to inspect the part and find out if it's within our tolerance. Now it turns out that this particular part, it's not an aerospace part, so I don't need something in 30, 50, 60 micron accuracy, right? So I'm trying to produce a part that's roughly a millimeter, plus or minus a millimeter. And I just want to see if the part conforms to that. So the process that we would employ here with the scanner would be to take the part, and I'm going to place it on a turntable. The turntable would kind of remind you of Grandma's Lazy Susan at home. And you'll notice that we've got some targets on the turntable. There's no targets on the part required, so I'm going to take the part, I'm going to stick it onto the turntable, and then if we can cut back to the computer for the scanning. Okay, so now for the scanning itself, the way that it works is that we literally put the part on the turntable, and we're going to start the scanner. And you can see that we'll zoom in a little bit. Right? So basically, as fast as I can move the turntable, I'm getting 3D geometry of the scanner. Or of the part, rather. And the process here to collect the 3D geometry is a little bit of just technique in terms of orienting the scanner at some different angles, kind of taking your time, and that should be enough for what I need, right? So within, about a minute, I've scanned the part. Now typically what I would do, honestly, is I would take the part and I would flip it upside down and I would scan the bottom of the part, and then I merged the top and the bottom together. And we'll show you kind of what that looks like. So if I go here and if I go here, we'll show you what the 3D scan merge of the top and the bottom of the part would look like. And then from here, we're going to go into Polyworks, and I'll walk you through the reporting process again so that you see that and you get to understand that as well. So here's what the 3D scan part looks like. So you can see that I scanned the top of the part that we just covered here a moment ago. Then I flipped it over and I scanned the bottom of the part. It's 3 mouse clicks to join the top with the bottom, and this is what I get. Now once I've got this, if I hit File, Export, Mesh, it allows me to export the part as an STL file. Now STL is familiar to you because that's what drives the 3D printers. It's also what we use inside of Polyworks in terms of being able to do the inspection report. So I would give the part a file name and I would hit save. Then from there I'm going to go into Polyworks. So this is what Polyworks looks like. Inside of Polyworks, it's really kind of a 3-step or 4-step process. It's really pretty simple to teach anybody, but just to kind of run through that with you briefly, I'm going to create an inspection report. The inspection report in the end is going to look something like this. So I wanted to show, this is a PDF, so I wanted to show here's what the CAD part looked like. On page 2, here's what the scan looked like. Below the scan, here's what the alignment between the CAD and the scan looked like. And then after that, I want to start getting into some measurements. Now, many of you may have seen reports like this from maybe some of your suppliers. And maybe you wondered how those reports were created. This is the exact process that they're going through. And so I'm going to run through briefly with you. This is, again, about a 3 to 5 minute process to show you how we would create an inspection report like this. So to do that, step 1 is to open up the CAD model. So I'll say File, Open, and here's the CAD model. So this is the net shape that Jeremiah 3D printed here a few minutes ago. So this is what the CAD model comes in looking like. And inside of Polyworks, I can open IGES, I can open STEP. If I'd prefer to work with CAD native data, They do have converters that you can acquire that would open SolidWorks native or CATIA native, or I think NX native as well. So there are a variety of direct converters. So step 1 is open CAD. Step 2 is to open up the 3D scan data. And I saved the 3D scan that we just did as link merge. And I scanned that in millimeters. So we'll open that up in millimeters. And you can see that the 3D scan data is kind of that gold-looking thing, and the CAD data is the gray-looking thing. Now, step 3 is to align the two. Now, if I had to do this in CAD, I'd probably spend the better part of the afternoon aligning two parts together inside of CAD. Inside of PolyWorks, it's literally a 3-mouse-click process. So I tell it that I want to measure in millimeters, and I say that I want to align the two parts. Normally, I would start with a best fit alignment first, and then if I have a drawing that defines different datums, then I would fine-tune the alignment to virtually any kind of a datum alignment. PolyWorks supports any kind of an alignment. And then we'll say close there. So now what I've got is I've got my part. I've got, again, the gray color or silver color is the CAD. The gold color is the physical part that I just 3D scanned. Now what I'd like to do is I'd like to create generically a color map. It kind of looks like, for those of you that you remember Bart's presentation with FEA, it was showing stresses and strains. So it's showing loading conditions, right? The color map inside of PolyWorks shows tolerances. So am I, how closely does the physical part match the nominal of the CAD data? Again, to do that, it's literally 3 mouse clicks. So I say create a color map and tell it to do a measurement. Now the color map is going to come in. It supports, any kind of color nomenclature that you want to use. Most of our customers want to use green for good, it's in spec in those areas. Red for bad, it's out of spec negative. And blue for bad, it's out of spec positive. So areas that you see highlighted in blue are extra material. And since I'm probably going to machine this, do one pass of finish machining, that's probably okay. Areas that are in red are potentially bad. But what I really want to show you is I want to do a measurement on here. So I want to say, well, my spec is really plus and minus 1 millimeter. So I'll say I want to flag anything that's 1 millimeter to minus 1 millimeter. So minus 1. And then we'll tell it to update that. So what this should show us now is how close we are to our spec. And you can see that we're really very, very close. The areas that are in green are within that spec. And for the function of this part, what's really critical to me are the holes, are the bores, because I'm going to press fit bushings into these holes. And so I might have to ream the holes slightly to finish them. And you can see there's extra material to do that. Once I've done this, then I can do some additional measurements, so we'll show you a couple. So if I want to measure the holes to find out exactly what the size of the holes are, I select measure, I say create a feature, and as I hover over the feature, it highlights it. If I left mouse click on it, it measures that cylinder. Right now it's highlighting that feature on CAD. On CAD, it's saying that that hole is a 19 millimeter hole. On this feature, we'll pick that one. Again, it's going to measure it on CAD. And then we'll pick this third one down here, right here. And that's another 19 millimeter hole. So then the next thing that I want to do is I want to say, well, that's what the dimension is on the CAD. What's the physical dimension on the 3D printed part? How close to that size is it? So to do that, you literally, this is just Microsoft Windows stuff. You pick the first one, you pick the last one, you right mouse click and you say extract the measurement. And now it'll go in and it'll look at the 3D scan data, it'll compare that to the CAD nominal, and it'll tell me what my deviation is. In the case of hole number 1 or cylinder number 1, the dimension is, the difference is 130 microns. So we're really very, very close. In the case of hole number 3, the difference is 135 microns. So again, very, very close to the exact right size. So now what I want to do is I want to create the inspection report. Remember I showed you this thing over here? So the question is, how do I create that inspection report? And the answer is pretty simple. I'll show you that quickly. So in my inspection report, what I want to do is I want to, let's turn those off. Let's turn off my color map. So I'm going to deactivate that. And then I'm going to sit down so I can see what I'm doing. And then I'm going to turn off the scan data. So the first image I want on my inspection report is the CAD data. So to put that into my inspection report, you literally hit the camera icon on the top bar of Polyworks. And it says, well, what do you want to call this? I'm going to say webcast. And my name is Frank. Good enough. We'll say add that, close that. So first I had the CAD data. Now I want to turn off the CAD data and I want to show what the 3D scan data looks like. This is my 3D scan. And again, I hit the camera. So I take a picture of the 3D scan. Then I want to show the alignment between the two. So now I want to right mouse click on the CAD and I want to take a picture of that. Then the next thing I wanted to show in my inspection report is the color map. So let me show you the inspection report, at least what we've created so far. So on page 2, I've got, here's the CAD, here's the scan data, here's that alignment. This is being just Windows stuff, it's all pretty intuitive. If I want all that on page 1, I'll delete that. On page 1, I want to have my logo, so I say insert image from a file, and I'm going to insert my logo. We'll just drag and drop it there. Now the images that are on page 2, I want that on page 1, and I'm going to center that on page 1. On page 2, I want to center that maybe. On page 3, I've got my alignment. I'm going to put that on page 2. Try and wrap this up here in about a minute. On any of these images, I can add text, so I can say, well, especially this is helpful if I'm dealing with non-technical people. So if I'm going to hand an inspection drawing to a manufacturing person or maybe a non-technical person that to try and help them understand what they're looking at, I can add some nomenclature in here. So I can say this is my CAD data. So I can go in and I can start adding simple notes to any of these views so that again, as people look at it, they can see what they are. I'll go back to my 3D model, and now I'm going to turn on the color map again. So I just say activate the color map. So the color map comes back on. Once the color map's back on, if I want to include a view of this in my report, again, I hit the camera. And then if I want to include what the nominal settings are on the inspection, I right mouse click on my color map and I say add the dimensions to my report as a table, so that if I go back into my report, I can see, well, here's my color map and here's my nominal parameters for the part. Right? So the point here is that I can take virtually any kind of a part, I can 3D scan it in minutes, I can create an inspection report. Now if I were doing this for a first article process, for example, if Jeremiah had printed maybe 5 of these and I wanted to make sure that the printer was producing consistent parts with consistent geometry and dimensions. I could scan 3 of these or 5 of these, however many he gave me, literally in minutes. I create this report just one time. I don't have to create it, you know, every 5 times. I create it one time, and then I scan part number 1, I say add that to the report. I save the report, and then I scan part 2, add part 2. Scan part 3, add part 3. So the point is, I'm not recreating the report for each one of the inspection scans. And so this comes into play for those of you that have a first article inspection process, maybe as part of your first article inspection process. If you're an aerospace company, you complete something called an AS9102. If you're an automotive or mobility, or really most industrial manufacturing companies, would generate something called a PPAP. So from this, from Polyworks, I can populate the as measured data into the AS9102 or into the PPAP so that I'm not manually rekeying that. We have another piece of software that we're not going to feature for you today, but it gives you the ability to create the AS9102 or the PPAP. You basically open up the PDF as you pick dimensions, it balloons the dimension, and then creates the PPAP. So as I pick, it adds balloon, 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 and then adds an entry for the dimension of each one of those features that I pick. So that may be something of future interest for a future webcast. The point is that inside of Polyworks, as I scan the individual parts, I can automatically add the as measured dimensions back in to the PPAP or the AS9102 without having to manually rekey it. Okay, so that's a little bit about the inspection process, leveraging a portable 3D scanner, creating the inspection in literally minutes to 3D scan the part, and then creating the report. Really, the magic happens at the reporting level. We can teach virtually anybody how to operate a 3D scanner. An engineer or a manufacturing engineer is probably going to use Polyworks. That's where the real brains of the process is. The 3D scanning is something that is more technique, and we can teach virtually anybody in your organization how to master 3D scanning. So with that, we want to go back to Tim for another minute. Tim's got some parts that he'd like to share with you so that you get to see some real-world customer parts as well, and then we'll come back to close over here.
So we've got a couple of examples of real-world parts. So this happens to be a mold insert, which has conformal cooling channel that actually goes in the part, spirals around to get water up into the tip. So this part is not able to be produced in conventional machining. Some of the inventory things that I talked about in my slides were basically end of arm grippers. These happen to be tool steel. So basically you can print these and complete wash and cycle in about a day and a half, 2 days. Our newest material is really interesting for heat sinks. So this is actually a copper heat sink material. We can also use this for welding applications as well. Different kinds of products that we've done for customers, they happen to have aluminum 6061 spec, but we actually built this out of continuous carbon fiber. So this part is very strong. And then we also made it out of metal. So this part takes usually four to 6 weeks to get delivered. So this sets a timing chain for an engine, and we're actually able to produce this part in 3 days. So very interesting approach to saving customers money, and we'll help build the ROIs with you for the technology. We can also combine our nylon material and have snap fits for any kind of applications that you need. So with that, I think we'll open it up to Q&A.
Back here for a minute.
Sure.
So let's go back to PowerPoint for a minute, and we'll kind of wrap things up. So in conclusion, a few key takeaways. What we tried to demonstrate is that generative design helps optimize product and part design. So starting with your product and part, if you're really looking to leverage additive Generative design really is maybe that potential bridge to help you for design for additive manufacturing. A lot of people, maybe you've heard the term DFAM, D-F-A-M, stands for Design for Additive Manufacturing. So the GDE is one of those tools that you could employ in your organization to really optimize the front end of your additive manufacturing process. Additive manufacturing, what we're running into very, very commonly today is people interested in employing additive for in-process tooling, jigs, fixtures, CMM fixtures, weld fixtures. There's 100 different applications. So as you look at maybe employing additive within your organization, just walk around your shop. Look at anything that is work holding, any place where I've got a part that I'm going to lock into a work holding piece to perform a drilling operation on, or whatever the case might be. We've got a great story to tell there, and the ROI in those applications is really very, very high. 3D scanning, we talked a lot about this for first article inspection, again for PPAPs and for AS9102. It's a home run there. I'd love the opportunity to work with you on that. Pre-production inspection and in-process inspection. What's becoming more and more popular these days is people employing the 3D scanners, including the one that I just showed you, and sticking it onto a robot so that I can quickly 3D scan something and not have to man or handle the 3D scanner. I can program the robot, and so if I want to do near-line or in-line inspection of products, I can make that a robotic task. Reverse engineering is something that we really didn't get into very much today. We've got customers, I think a great example is WeatherTech floor liners. I think everybody has seen their commercials where they talk about laser measured for accuracy and fit. That's exactly what our technology does. So in the case of somebody like WeatherTech, gives them the ability to literally go out to a parking lot with a scanner, plug in to a laptop, set the laptop on the car seat, and scan the inside of the vehicle. By the way, some of our scanners can be used outdoors in sunlight. They can be used inside in fluorescent. It doesn't really matter the environment. So reverse engineering is a huge application for 3D scanning. And then kind of in closing, we've got some end of year promotions going on right now, which are some variety of scanner and software, or scanner and 3D printing. We also have just 3D printing bundles going on right now. So if you're in a situation that you'd like to talk about maybe trying to save yourself some money before the end of the year, the factories are anxious to try and make things happen. As well as we have some demo equipment that occasionally throughout the year we're purchasing new demo equipment. We're offering our older demo equipment for sale, and you can see pretty much what we do with the demo equipment. We're in a lab, or we may be in a customer site, but it's not out getting beat up on a production floor. So our demo equipment is very pristine. We can offer it recertified. It comes with an ISO certificate, and it's metrology grade equipment ready to go. And then also, this kind of came to our attention just this past week. Our government is helping us a little bit with a offer that they call Section 179. It's basically a tax credit promo that the government has going for the year, end of the year. And so if you're in a position where you can leverage some cash to get in an asset that you need for the organization, you can also get a tax credit for the end of the year. And in closing, Adaptive sponsors, we have an annual customer conference. This year it's planned in April, and I guess we'll see if we actually do that in April, but it may become a virtual event. We may also elect to defer that until later in the year, but we do annual customer events. And really the value of these events is for you to attend and to network with your peers. Really your cost to attend this thing is just your travel and a day or two of your time. But it's a great opportunity to network with your peer companies and meet some organizations that are the same size as yours, maybe a little bit larger, maybe a little bit smaller, and gives you the opportunity to learn, kind of the good, the bad, the ugly. What works really well, or this didn't work for us, stay away from it. So it's really something that we offer to our customers to network and learn a little bit more. So with that, let's go back to just the live cameras, and we're going to take any questions that have come in via the chat. If you do have any questions, I think in the upper right-hand corner there's a chat window. Now's a great time, if you haven't been doing it since we started. Go ahead and type in some questions. We've got 10, 15 minutes. We'll take whatever and answer some questions and kind of go from there. If you don't have any questions now, you can certainly email us at sales@adaptivecorp.com, and we can address your questions later. Anything coming up on radar?
Yeah, what size parts are appropriate for HandyScan Black Elite?
So the HandyScan Black Elite, remember we talked about the right tool for the job? The volume, the ideal volume for this scanner is anything from about the size of a Microsoft mouse, maybe a little bit smaller, up to the size of a car door. So if I'm going to do really small parts, if all of my parts are the size of your ring and that's what you're going to scan, that's probably a different solution from us, different technology. If most of your parts can be described as roughly the size of one of these grippers or a Microsoft mouse, again up to the size of a car door, this thing is a home run. We have other scanners that if most of what I'm scanning starts at the size of a car door and could be the size of a car, the size of an airplane. We've done some service work for Lockheed Martin, for example, scanning the inside of a C-130. That involves some different equipment. So it's really very application dependent. The HandyScan is size of the Microsoft mouse up to the size of a car door, roughly.
What part features can be scanned for FAI?
Pretty much any part feature can be scanned for first art. FAI stands for First Article Inspection. So any feature that is line of sight that I can see on my part, I can scan. So if I have a part like this and I can see the features, then for sure I can scan it. If I have a part that has a hole that goes through and bores into the part and then comes out in some other blind area, can I inspect the internals of that part? The answer is the internals of that hole. The answer is no. Why? Because it's not line of sight. So to answer the question, for first article inspection, I can scan any features that are in my line of sight.
How quickly can a part be scanned?
Most parts can be scanned depending on the size of the part. This one you saw us scan it in about a minute. True, I didn't scan both sides. That was, so let's say that it's about 2 minutes to scan a part like this. If I put this part onto a CMM and just measured it on a CMM, it would probably run something like 20 minutes, maybe 30 minutes, maybe more. Depends on the type of CMM that I'm running on. So the speed difference is literally 20 to 30 minutes on a CMM. Maybe an ARM is 5, 8, 10 minutes maybe. A 3D scanner can scan the part in a couple of minutes.
What is the bed size of the Metal X?
That's a good question. Can we put the camera on the Metal X here? So basically we can see here is the print bed. The sheet is actually the size. So you're looking at about, and we actually overgrow the parts by 20% in the green state. So your actual envelope size of a part that you get delivered to you, since it will shrink or reduce by 20%, it's a little bit smaller than this build platform here. So we'll email you the details on all of the specifics. It also depends on which Sinter oven that we have. We have a Sinter 1 unit that is available, but we have the Sinter 2, which allows us to actually sinter larger parts.
And what is the accuracy of the scanner and what part tolerances are applicable?
Okay, so the accuracy of the scanner is 9/10 of a thou is what it's spec'd to, and it's certified to that, which in microns is roughly 30 microns, I think. So, and if you compare that to a CMM, most CMMs are going to, depending on the CMM is always going to be the highest accuracy measurement device that you can get. And CMMs are typically maybe 2/10, 3/10, somewhere in there. They're really very, very accurate measurement devices. Most arms are 7 to 9/10 of a thou. This is 9/10 of a thou. So in terms of parts, it really opens that up to a lot of options. And I also might mention that we have a lot of customers that employ what they call hybrid inspection. And hybrid inspection is defined as maybe this is an aerospace part. So if this were an aerospace part and it's got 100 dimensions that I have to inspect on it, maybe only 10 of those dimensions, maybe 20 of them have to be to a tolerance of 5/10 of a thou or something like that. So what a lot of our customers will do is that they'll take the 3D scanner, they'll do a first pass scan with the 3D scanner and get a thumbs up, get a green light on the 3D scanner. And then if the part looks good, then when they take it to the CMM or whatever their secondary inspection device might be, rather than inspecting 100 dimensions and running the part for an hour, now they're only going to inspect 10 or 15 or 20. So the part only runs for maybe 20 or 30 minutes. So hopefully that answers your question.
So we have another question on when will titanium be available? So basically we can print parts currently in titanium, but the material will be shipping for customer use Q1, Q2 of 2021.
From start to finish, how long did the bike part take to produce?
From start to finish, you want to?
So from 3D printing standpoint, what we're looking at was the print time was about 26 hours, I believe. Then we have a wash time, and then we have a Sinter time. So roughly about a week to produce the part.
All right, well, if that's it, we're coming up on close time. So on behalf of Additive Corporation and Tim and Jeremiah and our team here, we'd like to thank all of you for joining us today. Hopefully you found the webcast informative and useful. If this is something that is of value to you and you'd like us to see us do more content and you've got some ideas of areas that you'd like to learn more about, we'd love the opportunity to do this for you. We also do workshops. A lot of customers now are starting to open up. We used to do this kind of stuff often at customer sites. And if there's an opportunity to do that with you all, we'd love to do that with any of you. Or if there's some ideas for future webcasts, we'd be totally open to ideas. So again, on behalf of myself and our team here at Additive, thank you for joining us today, and we'll be in touch. Thank you, everybody.